Welcome everyone to week 3 of PMR of this PMRF TA session. Just a minute. Yeah, sorry about it. Just yeah. Okay. Welcome everyone to the week 3 of PMRF TA session for the NPTEL course Approximate Methods in Quantum Chemistry. Quick intro of mine. I am a PhD student, PMRF in the Solid State and Structured Chemistry Unit, SSU, at the Indian Institute of Science, ISC Bangalore. This is. Sorry, I'm just. Okay. Sorry about that. Okay. So I am a PhD PMRF student at SSU, ISC Bangalore, and I am the NPTEL-PMRF TA for Approximate Method and Quantum Chemistry course. And there are total 8 2-hour interactive problem solving sessions, and which occurs every Saturday 6 p.m. to 8 p.m. Today it is happening on Sunday 6 p.m. to 8 p.m. on 19th February because it was postponed. Okay, so in this week 3, basically we will go into the content of the week 3 of the course, which is mostly in using linear variation principle in chemical bonds, like in actually using in actual molecules when we use linear variation principle. And then in week 3 we also learned about we learned about molecular orbital theory, and we also learned about how to use this for your topic. Sorry about that. We also about diatomic and polyatomic molecules as well, and some approximations. So mostly, in this study PMRF TA session, we will go through all those concepts again, and we will try to do some extra questions, and if the time permits, and we will also send assignment phase already submitted. We will also go through the assignment solutions as well. So and if you have any doubts, you can ask. Okay. So first, let's just do a quick revision of what linear variation principle was. Okay. So in linear variation principle, yeah. So in linear just make my screen here. So now in linear variation principle, right. So as we remember, if we have to just this one. Okay. So for linear variation principle, the concept is that so we don't know the exact solution of our problem of our Hamiltonian. So one way in linear variation principle is we can do a linear combination of like some psi1 psi2 that we know, and we approximate our solution as a linear combination of this two one. Then we write our energy value, this as phi hk phi divided by this phi, and basically and then you can see if you do this here, and you can write this as C psi1 plus C2 psi2 and C1 psi1 plus C2 psi2. Okay, and if it, and what you will get is C1 star C1, we get psi1 plus C2 star C1 psi2 psi1 plus here you can get similarly C1 star, you get C2 psi1 psi2 plus C2 star C2 psi2 psi2. Okay, and here we will consider here like C1 and C2 are bigger, and psi1 and psi2 are also bigger. Right. So we can simply write this as C1 square psi1 psi1 sorry about that, there was echoing in the problem. Okay, yeah. So we have C1 square psi1 psi1 plus C2 square psi2 psi2 plus 2 C1 C2 psi1 psi2. Alright, and since these are real psi1 psi2 psi2 psi1, they are same, then we will do is we will do a phi hk phi now, and that is what we need to find. So just okay. Okay, so this we can solve as C1 psi1 plus C2 psi2 h cap C1 again. C1 psi1 plus C2 psi2, right? And again you can solve the C1 star C1 psi1 h cap psi1 plus C1 star C2 psi1 h cap psi2 plus C2 star C1 psi2 h cap psi1 plus C2 star C2 psi2 h cap psi2, and again C1 C2 are real and psi1 psi2 are also real. So what we get is C1 square, we have psi1 h cap psi1 plus C2 square psi2 h cap psi2 plus here I will just write this 2 C1 C2 psi1 h cap psi2. Okay. Now this basically these are some matrix elements, psi2 and psi2 psi2. We can write this as C1 square. Now we will take this as S11, C2 square as 22 plus 2 C1 C2 as 12, and S12 will be equals to S21 because psi1 psi2 are real. And here also we will write it as C1 square H11 plus C2 square H22 plus 2 C1 C2 H12. Right. So this is how we find all this now, and that's our energy value E, the radiation energy that we are calculating. That will be given as C1 square H11 plus C2 square H22 is 2 C1 C2 H12 divided by C1 square S11 plus C2 square S22 plus 2 C1 C2 S12. Alright, and basically we have two variation parameters. We have C1 and C2, so we can do del E right as C1 equals to 0. From there, if you differentiate, you will get this equation C2 times H12 minus E S12 equals 0, and then we have del E right as C2 equals 0, which gives you C1 times H12 minus E S12 plus C2 times H22 minus E S2. Is it correct? So then what we can do is we have two equations, and we can write it in our determinant form. Okay, so you can write this as H in matrix representation basically. Sorry, matrix representation. That is H12 minus E times S12, H12 minus E times S12, and H22 minus E times S22, and C1 C2 equals to the relative as 0 0. Alright, now to solve this for this matrix equation to have a non-trivial solution, the determinant of this matrix, this has to be 0. This determinant has to be 0, and thus this way gives us our singular determinant. S22 minus E S22 equals to 0. Okay. And so basically you just have to solve this determinant, and you will get your values of E, and those are your energy, that are your energy values, and then using those E values you can just put them in these two equations. Where C1 and C2 you have to find. So basically just put them back in these two equations. The values of E, you have H11 S11 you have found. We have E values, and using two equations you can find two variables. And similarly, now we can have a combination of, similarly as you know, we can have a combination of I power 1 by n, and I power 1 to n. You can have like in this case, it is for like if you have just two wave functions, a linear combination of two wave functions only. But if you have more than two, then similarly like this, for 2 we have 2 cross 2, and for if you have n, then you will have an n cross n determinant that you might have to solve. Okay, and this kind of determinant. Okay, so that kind of determinant also you will have to make to 0. H12 minus E S12 and so on. You will have H1n minus E times S1n. Similarly, now H_n. Okay, and then this is H1n minus E times S1n. Sometimes here we can take this as ij equals to del of ij in those cases where our they become orthonormal, psi ij is orthonormal. So in those cases we can make this, and you can make this S11 in those cases will become S11 and S22. They will become 1, and S12 will become 0. So the calculation just becomes simpler. So instead of writing it like this, if I say that Sij is equals to del of Ij in this case, then our determinant would be simpler. It depends on the kind of problem that you have. But I can write this like this. Times minus e. So h n minus e. And I can write this h12, h2, h12, and h1n, h2n. Because we are taking okay. So this is basically a quick revision of what linear addition principle is. Generally, the questions that you have solved is for 2 plus 2 separate determinant, and you can have a combination of n orbitals that you can try wave functions are n. Try wave functions. Okay, maybe basically we can have our try wave function as this kind of as well, and combination of n linear wave function, and then you have to solve an n cross n set of determinants. This is a quick revision of what the linear addition principle was. Okay, let's just move on to now then. In this week, basically what we did is, in week 3, what was done is, we just used the traditional bond treatment for the H2 molecule. Okay. So, if you apply this for an H2 molecule, now for an H2 molecule, I will just write this equation because there's just actually a quick revision part only for this. So, your Hamiltonian for this H2 molecule will be something like this. I equal 1 to 2. Alright. And then do a minus. Del square by 2 minus summation over A equal 1 to 2 1 by R1A. This is the Hamiltonian for your hydrogen atom plus 1 by R12 plus 1 upon R AB in atom. Okay, for your H2 molecule and atomic units. So this will be a Hamiltonian. Now to solve this, we can take one 5 function as one SA of 1 and one SB of 2, which is like having two hydrogen atoms, one atom A and atom B. Atom A having electron 1 and atom B having electron 2. Phi 2. One SA2 and one SB1, which is again atom A having electron 1 and atom A having electron 2 and atom B having electron 1, and then our S function, phi function, will be a linear combination of this C1 phi1 and C2 phi2, and then we have to again solve the same H11 minus E S11, the addition principle that we just revised. E S12 H12 minus E S12. Again, this psi function S orbital function they are here, and C1 C2 also get associated here, and S22 minus E S22. This you have to make 0. So you have to solve this determinant, and as we solved at last, so. This matrix elements you will get is 1 minus 1 plus J in the atomic units. J will be equals to H22, and H12 will be equals to minus S square plus K equals to H21. Alright, and similarly you will get S11 equals to S22 equals to 1, and S12 equals to S21 equals to S square. Alright, so this has been done in the class, so that is just a quick revision, and using this you determine this energy value. One thing that I will point out is this Coulomb integral terms. So just since Coulomb integrals, let's just discuss with one what this J integrals look like and how to just see like this is a J integral. So like J integral in this case was coming as 1 SA star of 1 minus 1 upon R1B and 1 SA of 1 D of R1. Okay, so this is the integral. So last part is not. So basically, we are saying it's to be Coulomb integral because we can see that this. Okay. If we see these two terms, 1 SA star and 1 SA1, so this represents the electron 1 being in the atomic orbiter of atom A, 1s orbiter of atom A, and 1 RB. Okay, and 1 RB. That is our basically you can say operator or something operator. So that represents, so this term kind of represents the interaction of the electron density on atom A with the nuclear charge on atom B. So this is kind of a Coulomb integral. And one way to just to understand, okay, just by looking, because sometimes Coulomb integrals could be little complicated. So one thing you can do is you can take this complex functionals. This like you have one as a star functional. Like for this example, in this third integral, we can see that okay. So what we can do is this is our operator in the middle, where our operator is, and then we have this functions. We have star functions, and then we have 1SA1, 1SA2. Here we can see that electron 1 is in like atom A and electron 1 is in atom A again. Here also on the both side electron 2 is in atom B only. So there is no exchange is happening in this case. So this is kind of a Coulomb. That's why this is called Coulomb integral. From this you can say, and then in the third term also we can say that the electron density on electron 1 is on atom A and electron density of electron 2 is on atom B, and then they are interacting with kind of each other. So that is also Coulomb integral. Although this is explanatory, but just to in case if someone gets confused in how to determine if you get confused like how to determine if it is a Coulomb integral or not, you can see that okay, on both sides of the operator the atom is A for the electron 1, and here also for electron 2. So for atom 2, on the both sides it is atom B, and similarly here as well. For middle operator, on the both sides for electron 1 it is atom A and atom B. So that is just like for the K term as well. If you solve the K term, so K term, I guess. All the form will change as according to the wave function and the Hamiltonian, but it is just an observation that can help during complicated terms. VR2, and then we have 1SA So here also you can see like this is our whatever our observable operator is, and on the both side we have our wave function, and the electron one here it is in atom A, while it is in different wave function. So there is some kind of an exchange of electron is happening, and similarly in this this one as well, you can see that if you compare these two green ones, then there is one S of A star. So there is an exchange of happening. The electron one is in A here, it is in B here. So there is some exchange. So this comes under kind of an exchange integral. We can't explain it in terms of a kind of a Coulomb integral. In Coulomb integral, the electrons are within the same wave function on both sides, and exchange, there is an exchange of which exchange has happened. So this is just an observation. There have been complicated exchange and Coulomb integrals to see on both sides how the wave function, how the electron is going. Is it in the same wave function or not? Alright, and this, solving this, we can get this E plus E minus values that we got on the class itself. So I will just write it G plus minus K upon 1 plus minus S square. And similarly, you can get this 5 plus minus. Let us write without an operation constant. This calculation could be solved easily, and then again, as you know, this 5 plus will be our ground state, but again, this is not a spin statistic. We need our electronic wave function to be antisymmetric, and from there we move on because we know that if we apply P cap, now phi 2 will have the lower energy. The ground state, we know that ground state comes as 5 plus with energy E plus, correct? And the energy is minus 1. Plus so your ground state is coming from E plus, and that is your ground state. But we need our wave function plus a primary wave function. It has to satisfy the antisymmetric principle. And if you apply P cap on 1.5 plus, then that doesn't give you a minus sign. So for this, we multiply the wave function with an because we have not considered the spin of these of the electrons, of these two electrons. So LBA wave function will be given by a combination of this 5 plus times spin wave function as well. For that, for first, let us just do some spin, what was done in the spin statistics. We revise, and we will also solve some problem regarding this as well, regarding the spin statistic. So now we know that if we apply S gives us in this momentum, we know that this is S into S plus 1 and H plus square alpha. Alright, and then you can have another spin state which will be S into S plus 1 H plus square times beta. Okay, and we have S square of Z alpha is equals to H plus I2 alpha, and S plus Z beta equals to H plus. Okay, now let me just write it as MS, so that this MS H plus times alpha and MS H plus times beta. Alright, now for electrons, S is equals to half. because these are half spin particles, so s equals to half, and our ms comes as plus minus half and plus half, because ms will be from minus s to plus s. Alright, so for this, this is for the electrons. Just for electrons. Can I just we'll just do a quick questions on that is done. Okay, now we have like for 2 electrons. If we have a 2 electron system, we will have s cap is equals to s cap 1 plus s cap 2. Alright, now then in that case what will happen is that our s values will go from s1 plus s2 to mod of s1 minus s2, and since here in our case we have s1 is equals to s2 equals to half, so we know our s value are equals to 0 and 1, and our ms values also we know will go from minus s minus s minus s plus 1 to s minus 1 s, and since again we have just 0 and 1 value, that gives us ms equals to for 0 0 and plus 1 minus 1. Okay, so there will be like 3 values, 0 plus 1 minus 1, and from there we have our eigencats. Here see there will be 0 0, there will be 1 0, there will be 1 1, there will be 1 minus 1. We will have this kind of 4 kind of wave functions, which we will represent as 1, 1 is represented as this is represented as, so 1, 1 so 1, 1 is represented as alpha 1, alpha 2. So basically you can understand 1, 1 means the s value is 1 and the ms value is 1 for that s, and that we are considering that is represented by alpha 1 alpha 2. So both the spins are parallel of the electron, and we have 1 minus 1. This is represented by beta 1 beta 2, and 1, 0 is represented by 1 by root 2 times alpha 1 beta 2 plus alpha 2 beta 1, and 0, 0 is represented by 1 by root 2 times alpha 1 beta 2 minus alpha 2 beta 1. So, and this as discussed is our quantum triplets. They will have the s equals to 1 and they are symmetric. And this is our singlet. This is for s equals to 0 and this is antisymmetric. So our well-behaved function, as we know, our well-behaved function psi function will be given by this phi plus, which is our ground state, and this 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. Okay, and now if I apply this pk12, which is our commutation operator, on this side, it will operate on phi plus and 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. Okay. Now to apply this, and 5 I will apply on this, so 5 plus is given by 1 I say 1 as we written, okay, so 5 plus, they are just plus and combination to ignoring this ignoring the normalization constant, 1 sp of 2 plus SA of 2 and SP of 1. Alright. It is given by this times whatever our value 2. Alpha 1 means like this is the alpha 1, electron 1. This is beta 2 minus alpha. The electron 2 has this, because it is in this kind of spin, it has alpha spin, and this has beta spin. Alpha spin, beta spin, because you know that 2 are going to spin plus up and minus. Spin up and spin minus, we are representing them as by alpha and beta spin for the electrons. Now this operator will first act on 5 plus, and okay, so this is, it will act on both of them. And when it acts on this, we know that this will give me the same. Here I just have to interchange 1 and 2. And here also I will interchange within this spin wave function as well. Alpha 2 beta 1 minus alpha 1 beta 2. Alright. So from here I can rearrange this thing. Minus A1 minus P2 plus minus A2 1 SP1. This is our 5 plus only. And this will give me a minus times minus 1 times 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1, and thus what we get is minus of, we get 5 plus times minus of our wave function, that okay, basically we get a minus sign, so we get a minus sign of this side, and that's how our wave function is antisymmetric. So that is antisymmetric. Alright, so this we have explicitly proved that it is antisymmetric, so that combination of these multiplication is antisymmetric. Now let us also do some questions, something which is similar in assignment as well. So so basically, for example, if we have to solve this escape square times beta 1 and beta 2, okay, so we have to solve this kind of a problem. Then you have escape square. Now beta 1 beta 2, you just have to check that okay, beta 1 beta represented means that we have s equals to 1 and our ms is equals to minus 1. That is what beta 1 and beta 2 represent. And then we know that is just equals to h cross square times s into s plus 1, 1 into n plus 1 times s equals to 1 and m is equals to minus 1. That is here equals to 2h cross square, and we can identify beta 1 beta 2. Alright, so that is just how to solve this. This is similarly you can have escape z acting on this beta 1 beta 2 as well. Okay, so in that case, basically you are applying this on just convert it into this in this forms. So for this question, just convert it into this kind of forms, what this is, and you know that it's h cross times ms. Ms is minus 1, so we have minus h cross, and then you can just write it as whatever you are s equals to 1 and ms equals to minus 1. This becomes minus h plus beta 1 comma beta 2. Alright. So basically we can find in this way we can find this values for each one of them. Like similarly you can find it for escape square on alpha 1 alpha 2. If you do escape c on alpha 1 alpha 2, again alpha 1 and alpha 2, then basically that means we have escape z acting on s equals to 1 and ms equals to 1. Right, that is your alpha 1 alpha 2. That will be equal to H cross type ms is 1, s equals to 1, ms equals to 1. So that will be H cross times alpha 1 alpha 2. Alright, so this is how this is kind of how we have to solve if for this spin states. We have to find escape square and escape z. Alright, so this completes this revision. Okay, what we got in the wave function in the valence band treatment of H2. Okay, and okay, so now then what we do the molecular orbital theory of this for the H2 plus, and then we do the molecular orbital theory for the hadrons. Let me just quickly go through that as well. Now for the H2 plus, the Hamiltonian that you will have is Rn minus 1 upon Rb plus 1 upon Rab. Alright. And here the kind of wave function that we used were phi 1 is equals to 1 SA and phi 2 is equals to 1 SP, because we have basically we have this is the Hamiltonian for we have the Stirling electron. This is for H2 plus. Okay, this is the Hamiltonian for H2 plus, and we consider 1SA and 1SP, and our phi function we consider as C1 phi 1 plus C2 phi 2, and similarly as it has been solved in the class as well. Basically, you have to solve this again. We have to solve this determinant. And what that has been formed. So solving the questions in the basically this has been solved in the class. So that is just a quick revision. So okay, what happens in this monotropic theory, and from there we obtain this E plus and E minus. Alright. I will just I will not go into detail because this has been done in the class, so I will not go into this detail. But you get this plus minus s values, and you also get this 5 plus minus root of 2 times 1 plus minus s 1 sa plus minus 1 sp. Okay, we just have to solve that in the similar way. We will have the similar Coulomb integral term and the exchange term. Now, in this case, again you will have bonding and the anti-bonding orbitals that we obtain. So, what is the benefit of this molecular theory is that basically we can now say that we have two 1SA orbitals. Let's say we bring 1, 2 SA orbitals, and bring them near. We first make actually this molecular orbitals. So initially what we did earlier for the H2 molecule, we did this linear combination of the atomic orbitals kind of thing. Like we took the atomic orbitals and we made a linear combination of those atomic orbitals which were involved, which was 1SA and 1SP only. Here instead of that, what we are doing is we are making the molecular orbitals using H2 plus, and then we will put our electrons. Like for H2 plus we will put like 1 electron, and for H2 we can put two electrons, and thus we can form this kind of, we can using this molecular play you can do for H2 molecule you can go to H2 minus as well. 1 electron will go to the anti-bonding orbital. This will be your bonding antibodies. This will be sigma bonding orbital, and this will be sigma star anti-bonding orbital. orbital. Okay, so this is just a quick revision here. And as was shown in the class, if you write this here, this 5 molecular orbital, then what you will get, which is basically so basically like for H2 molecule, using 5 plus minus of H2 plus molecule, I can write my 5 molecular orbital as 5 plus, the electron will go into 5 plus, as I say electron 2 will also go to 5 plus, and remember that we have to multiply it by some spin wave function because we have to make it anti-symmetric. So I will multiply it by some spin wave function, let's say chi. We multiply it with our wave function. Okay, so the complete wave function of this H2 molecule, and correct with varied wave function. Varied wave function for H2 molecule. This is our varied wave function. So just to point out here that you have to write the varied wave function, and you have to multiply this with your because you know that pk of 1 2, if you do here again from 5 plus of 1 also, what you're going to get is what you get is plus 1. Okay, so you have to write this anti-symmetric spin wave function, which will be alpha 1 beta 2 minus alpha 2 beta 1. So this is, I just want to point out that the varied wave function will have the spin part included as well. Okay, and similarly as it has been shown in the class. So so as it was shown in the class, now that is just for the spin part, but let's just consider this part only. This is the main part, but this is for the anti-symmetric requirement. It's for the anti-symmetric requirement. Anti-symmetric requirement. So just remember that we have to multiply it here later. But if you just open this 5 plus 5 minus, let's just consider this 5 plus 5 minus, which was considered in the class. So you know that this thing will open into a 5 ionic plus a 5 variational bond treatment, what we got from the variational bond treatment. What this 5 ionic one basically looks like. So just a quick understanding. So what will happen is that your 5 ionic will look like one SA of 1, one SA of 2, plus one SP of 1, one SP of 2. So if you see each of these terms, so these terms look like we have a hydrogen atom A, and now you have hydrogen atom B, and according to this equation, what will happen is both the electrons, when at r tends to infinity, both the electrons will go to atom A, or what could happen is both the electrons can go to atom B. This kind of dissociation is called ionic dissociation. So from your ionic and variational bond, you get at r infinity, we are getting two kind of dissociation. Similarly, from 5 variational bond, which are written by one SA of 1, say of 2 plus 1 sp of 1 and 1 sp of 2. If you go to r tends to infinity, this will now look like okay, 1 electron at here and 1 electron here. Similarly, from here, I guess I have written something wrong. Okay, sorry. It's corrected. Let's say 1 sp of 2. Plus, let's say 1 sp of 1. Alright. So here when at r tends to infinity, what will happen is you will have one electron at atom A and 1 electron at atom B, and here you will have 1 electron at atom B and 1 electron at atom A. Alright, and this is called the bi-radical dissociation. Now, this is predicting equivalent ionic and bi-radial dissociation. But in experiments, and you can but in experiments it is known that experimentally. So I just want to just find out here that experimentally always this bi-radical dissociation. So this is where, as discussed in the class, this Merkel orbital theory is not giving us the correct kind of the answer that. It is always bi-radical dissociation, and here where our Merkel orbital theory kind of fails, because it gives like as it said in the title, it gives more of the ionic character, while the additional bond theory for H2 molecule that gives us, but it doesn't give. So we need to use some more advanced theory to get the quantitative results. I just want to know what this bi-radical dissociation is, and this bi-radical dissociation is actually the one that experimentally occurs. Then, okay, now let us move to some different type of question. Okay, now then we use this Merkel orbital theory for the treatment of the polyatomics. So let us do a question and understand this thing, this Merkel orbital theory. Okay, so let us again revise for the polyatomic system the approximation that has been used. So the approximation, because you know that okay, for as discussed in the class, like if you have so many valence electrons and we have like we just revised the variation principle, we know that if we have like n electron, we have n valence electrons. You can say okay, we just consider valence electrons only, because we don't consider the co-electrons and the core orbitals and the virtual orbitals. And even for the valence electrons as well, if we have like for we just have this two kind of electrons. So that if we did in this, we just did for this variation, this variation principle, we know that if we have like two wave function only, like if we have two valence orbitals only, then we will have 2 plus 2 separate determinant. Okay, but if we have but we can have an n plus n determinant if we have this n wave functions of linear combination we are doing, or you can say there are n electrons or n valence orbitals. Now to reduce our problem, we can this is the kind of the approximation that I have discussed in the class. So, what we have discussed in class. Just like what was discussed in class first. If we have psi I, h cap psi I, there will be, which is h I j, will not be equal to 0, and psi I psi j will not, which is equal to s I j will not be equal to 0, only when the atomic orbitals have same symmetry species in the one group of the molecule. Right. And as we have seen for the, let's say for the example of, so we are taking the example of the O2 molecule. So this is the approximation that has been used, and now we will solve this problem, and hopefully with this you will be able to use this approximations to find the ground state of this oxygen. So first, so what does this give is as we have seen, so if you go into the points of symmetry and for the O2 molecule, okay, we will just solve our problem. So our problem is basically we have to determine the ground state configuration and bound orders of molecular oxygen. So let me just also give an intro what is bound order. Bound order for this problem, let us see what bound order is. Bound order of a diatomic molecule is defined as half the difference basically, so you have to give your boundary represented by B, then B is equals to half of number of bonding minus number of anti-bonding molecules. Okay? Bonding molecule. This is the definition, and it also gives it is an indicator of strength of it is an indicator of strength of the bond. So now we will solve our question, and hopefully we will be able to understand what all this thing is. Okay, so this is our problem that we have to solve. Okay, now as you have seen in the class, basically um, to find this ground truth and using this approximation that we are taking, that uh, this result, that basically the main result that we are seeing, that only when the species they have the same symmetry according to the point group of the molecule, then only our analysis. So because of this, what we can do is we can separate out our orbitals. Like for example, let's start with our oxygen molecule. So we will start with O2 molecule. For O2 molecule, okay, we have. So if you see, we have in total we have 12 valence electrons, right? So for oxygen, you know that we have 1s2, 2s2, and 2p4. So and these are our valence electrons. So this is what we are going to solve for. So we have 12. We have in total 12 valence electrons, and out of them, we know that okay. So one sum will be 2s, and so the orbital that we have is 2p2z. Now out of this, according to the point group symmetry of this point group of the molecule, O2 molecule, we have 2s, 2p, we have the sigma symmetry. So I will write it as symmetry. What is the symmetry? So 2s, 2pz have the sigma symmetry, and these two orbitals 2p, x, y, they have the pi symmetry. They have this kind of this pi symmetry. So now because of this, what we know that now 2s and 2pz will combine. 2s and 2pz will form 4 molecular orbitals, which are going to be 1 sigma g, 1 sigma u, 2 sigma g, and 2 sigma u. And this 2px and 2py will form which are sigma orbitals and pi orbitals. This is 4 molecular orbitals, because that is the main basic thing, right? Since they have the same symmetry, so they will form 4 other molecular orbitals, which will be our 1 pi u. It will form actually two molecular orbitals, 2 other degenerate molecular orbitals, actually, because these are already degenerate, so they will to degenerate molecular orbitals, 1 pi u and 1 pi g. Okay. Now, so basically 2px and 2py will combine independently. We just consider that they are combining independently, and this 2s and 2pz we consider that they are combining separately. So I will have this. Let's say I will have my 2s. Okay, so this is the diagram. So I will have my 2s here from one oxygen atom, and then I will have my, I will say this is my 2pz only. Okay, so I'm just taking 2pz here. Similarly, I will have this 2pz from this oxygen molecule, and I will have 2s from here. Now they form this kind of molecular orbitals, and all these four are going to be the linear combination of this 4 molecular orbitals from these 2 oxygen atoms. Alright. This will be our 1 sigma g. This will be our 1 sigma u. This will be our 2 sigma g. And this will be our 2 sigma u. Alright. So this will be the energy levels here. And then for this, we'll draw them with our red color. Then we will also have this other orbital, which are 2px and 2py. For the pi orbitals, 2px and 2py. And they will form, since they are degenerate, they will also form some degenerate energy levels. And we have this. This will be our 1 pi u. This is our 1 pi g. Now, here I have to point out that now this so as you have seen here, this sigma, when you have sigma and g, so sigma with the g, that will be a bonding orbital. These are going to be bonding. Sigma g's are bonding orbitals. And for pi, what will happen is this 1 pi u will be a bonding orbital. For pi, if we have u, then that is a bonding orbital. And let's say with yellow, I will represent this anti-bonding orbitals, and this will be our anti-bonding orbitals. This will be an anti-bonding orbital, this will be an anti-bonding orbital, and this is also an anti-bonding orbital. Now the energy levels for the sigma orbitals, the energy levels are actually if you have this kind of molecules, basically for as has been shown, this is the experimental data. This is the experimental. We have experimental result here. So from experiments and only from experimental, or you can say these are actually, you can say from the calculations as well. So not even experiment, like from calculations, you can say that these are okay. This is basically the data that we have for lithium to nitrogen, and then from oxygen to fluorine and neon, oxygen fluorine. So basically, as you can see, this sigma orbitals, they have less similar. Like there will be sigma g, which is the most bonding orbital. This is the most bonding orbital, and it has the most of the contribution will be from. Okay, it looks like the contributions are from sigma 2s only, but actually the contribution we will consider from, okay, in this one, okay, we'll just combine it here. The contributions comes from all the orbitals as has been shown here. So this sigma, this so when I draw it in the start, okay, so the sigma g and sigma u, they have the contribution mostly from the 2s orbitals, but in reality they will have contribution. So this 2s will have contribution here as well, and this 2s will have contribution here as well. Similarly, this 2s will have contribution here as well, it will have contribution here as well. Similarly, this 2pz will have contribution in both of these two. Okay, so basically there is contribution from this 2s and 2pz, and this will also have contribution here. initially when I do, I was saying that the sigma G, sigma U, which are one as sigma G, which are like most bonding orbiter, and then you go with anti-bonding. So they will have most contribution from this 2pz, but in reality the contribution will be considered from all of them. So it will be something like this, and this will be something like this. Similarly, there will be this contribution, and there will be this contribution. Yes, I should have just. This is your 2s, this is your 2pz, 2s and 2pz. So these orbitals, they are formed by all of them. So this actually you should remember. So they are being formed by the linear combination of all these 4 orbitals, 2s and 2pz. So the main diagram will be like this, and this is how you form for the oxygen into molecule. And if you go with these the energy value from the experiment, then this is the result that we have. And for oxygen, you can see that sigma orbitals, they have this thing there. You will have sigma G, you have sigma U, and you will have 2 sigma G, and then you will have 2 sigma U. And then similarly for pi, you will have the bonding orbitals will have the lower energy, 1 pi U. Okay, so in this diagram you can see bonding always have the lower energy. Bonding always have the lowest energy, and then you will have the anti-bonding energy, which is the higher. Now the only difference that happens is that where this pi and pi will go within this sigma range, okay, where pi u and pi g is there. So that is calculated using experiments, and there we have this this diagram that we have to use. Now for the oxygen molecule, we know that the sequence will be this. So for oxygen ground state, using the diagram above. So I made this calculation because it was done in the class as well, but mainly the thing is they will combine independently. This like the one having this sigma symmetry and then having this pi symmetry, and then they will form this sigma and pi bonding and anti-bonding orbitals, and accordingly they will have their energy levels. And the only thing that we don't tell from here is that where this pi bonds will go in the corresponding to this energy levels of the sigma. For that we have to do some experimental calculations, and that is given in this above diagram. So using the above diagram above, ground state, of O2 molecule is, you can write the ground state. So how are we going to control ground state now? So basically this is just how this molecular orbitals will form, and then we will use this diagram and see that okay, they will arrange in this energy levels, and then we will start filling the electrons from the lowest energy level. So we know that from here, from this diagram, we can see that the lowest energy levels are actually 1 sigma G. We have 1 sigma G and 1 sigma U. Sigma G. We will put 2 electrons into the sigma G, and we will put 2 electrons in our sigma U. Then we will put our 2 electrons in sigma G, and then we put our we will have 1 pi U, and 1 pi U we will put our 4 electrons. and 1 pi g, we will put our 2 electrons. Why I'm putting 4 electrons? Because we have like degenerate, these are degenerate states, so there will be 4 electrons. So for O2 molecule, if I have to write how this O2 molecule look like, just give a second. Alright, so for O2 molecule, our electron will go something like this. Okay, we have 2 electrons here. Okay, this is our lowest energy. Then comes a sigma u, so we will put 2 electrons here. Then it will be ours again sigma u, then the energy level is sigma g, so we will have 2 electrons here as well. Then the energy level comes 1 pi u, actually, so 1 pi u will come here. Let me see if I can. Okay, so what will happen is this energy level will be a little higher. What you are seeing is this is a little higher. Size. So you can basically see that this energy level will be somewhere here. This will be higher than the sigma g. So I read it and let us bring it. Just bring it here and. It's better to keep it separately. Okay. Sorry about that. I thought basically, okay, let's just keep it right here only. Okay. So you had 2 electrons will go here, and then according to energy level, you will have 1 pi u. So you can see this diagram, and you can see that 1 pi u has higher energy, 1 pi u. Then comes the pi orbitals, and then the sigma u. So in 1 pi u you can fill 4 electrons. So you can fill 4 electrons here. I will fill 1. So I will fill 1, 2, 3, 4 electrons here. And then you have to fill pi g orbitals. So there's interesting like these two will go parallel. Okay. So there will be a parallel electrons. So this will come in parallel electrons. That is happening because to avoid any electron-electron interaction, because you can fill here 4 electrons again because they are degenerate states. So you have 2 electrons in each of these orbitals, so they will go into the separate orbital. They will not go into the same orbital. They will go into separate orbitals to decrease the electron interactions. So there will be this. This will be our ground state configuration for O2 molecule. And now from this only we can calculate our bond order. So for bond order, if we have to calculate the bond order for O2 molecule, bond order, okay, for O2 molecule, let us calculate here. So that will be given by, we will have, as you can count, we have 2, 3, 4, and 8. We have 8 bonding orbitals, bonding electrons, and 4 anti-bonding electrons, which gives a bond order of 2. And we know that O2 is a diatomic molecule, so yes, bond order 2 gives us the idea that it is a in this there are 2 bonds between the oxygen atom. Now we have to do the same configuration bond order we had done for the oxygen atom. We can now do O2 plus, O2 minus, and O2 minus as well, just using the same electronic configuration. So I just do that. So ground state of O2, I just do, we can now just go to O2 2 plus, so we just don't have to do anything, we just change the electron configuration. So what we do is O2 plus will have now O2 molecule that has the 12 electrons. Now there are 12 valence electrons, 12 valence electrons. Now here for O2 2 plus we will have 10 valence electrons. So this electron configuration will come sigma G2 1 sigma u2, 2 sigma g2, 6, 7, 9, 10. So we will have 1 pi g orbital will now be empty. Now our bound order for O2 plus will just become half of 2, 3, 4, 8 minus 2 is 6 by 2, which is 3. So it is for O2 plus it is becoming 3. So as you can see, O2 plus is 3. Then and then ground state of similarly for O2 plus, it will O2 minus and O2 minus. Molecule is we will have 13 valence electrons here. So our one extra electron here you can see. Our highest is alright, so and from here our bound order for O2 minus will be half of 4, 8 minus 5, and it becomes 3 by 2 is 1.5. Similarly, we will have ground state of O2 minus molecule is, and then we will have 14 electrons. Then we will have 1 sigma G2, 1 sigma U2, 2 sigma G2, 1 pi U4, 1 pi G4. We will have 2 electrons here because this is pi G. Okay, now so bound order of O2 minus equals to half of 3, 4, 8 minus 6, 5, 6, we have 2 by 2, which is equals to 1. Okay, so from here we can see that O2 plus is the strongest bond. This is the strongest bond as well, because bonded loss is varying the strength, so which is strongest bond, and that you can understand as well from the terms that we have now the plus charge numbers of the positive charge because the cation the bond length will be less, so and from bonded as well we are getting that this is the strongest bond. This is our first question, and just by using this so basically using this idea that we discussed in the class, we can find these electronic configurations of how the electrons will go in these molecular orbitals of oxygen, and not only oxygen, O2 plus O2 minus also we can do, and using bond order we can find the strength of these bonds. Second part is the ground state of O2 singlet or triplet. Now as we discussed, when we put this 2 electrons at the end in the O2 molecule, then these 2 electrons will go into 2 different orbitals of 1 pi G. Right, 1 pi G. So from there we can see that these two are the valence electron that we have, they are parallel. So we have a non-zero spin that we get. So our ground state is actually going to be one of the triplet states, because in the singlet same state they are anti-parallel to each other, but these are going to be parallel. So our ground state is going to be a singlet. Interesting finding also that we can do, so we can find that as well just by looking at this configurations. This is our part A, part B, because of since only 2 electrons will occupy this last 1 pi g orbital, so as I said, they will be in a separate orbital and have the parallel spins. Ground state. It's predicted. Here. So it will be a ground state triplet. And one interesting fact, that is why interesting fact that this position of this non-zero spin. So although these are like we are being very qualitative calculation, but you can see that what other things this qualitative calculation can give. So we know that ground state of the O2 gas that is going to predicted to be triplet, and that actually explains this thing experimental result of the position of non-zero spin is consistent with the paramagnetic character of function gas technology. So although these are like qualitative stuff that we're doing, but they also gives us some idea about some experimental findings. Now let's go to the C part, which is determining the HOMO-LUMO orbitals in the case of O2. So as you can see, HOMO-LUMO orbitals is HOMO is the highest occupied molecular orbital, and LUMO is the lowest unoccupied molecular orbital. So using this, you can also find this HOMO-LUMO. Highest occupied and LUMO lowest unoccupied orbital. So just by this definition, and looking at our now for O2, data point for O2 molecule. Automated, you can see that from this electronic configuration that we have, the ground state configuration, we have the ground state our configuration is, we have 1 sigma G2, right? We have 1 sigma G2, and we have 1 sigma U2, and we have just take this actually. just let me just write it again. Okay, so what I have here is we have here. Okay, so to find your homo robot, let us again write this 1 sigma g, we have 1 sigma u, and we will have, just going to do this diagram, 1 sigma g, 1 sigma u, and we will have 2 sigma g and 1 pi u, 2 sigma g and 1 pi u, then we will have 1 pi g and 2 sigma u. G and 2 sigma u. Alright, and for if you have 12 valence electrons, we will go 2 here, 2 here, 2 electrons here, 4 here, and 2 electrons will go here. Alright, so just looking at this Brownian configuration, now we go to HOMO, which is the highest occupied molecular orbital. Now, highest occupied orbital is 1 pi g, so it is going to be 1 pi g, and our HOMO orbital, which is the highest unoccupied, so this 1 pi g is transfer, and only the highest antibonding orbital sigma, that is 2 sigma u, that is only unoccupied, so HOMO is 2 sigma u. Alright, then so we can find HOMO orbitals as well, like this, and then we can determine the ground state configurations. And okay, now another thing is that only like using the diagram itself, so we will just use this kind of, so we can basically you understand that how to make how these diagrams are forming, actually, as I've done in the class. So sigma g and pi u, that configuration happens just because of the bonding and anti-bonding character. That's why we have the energy level for sigma and pi, and how this sigma pi will be with respect to each other, that is given by some more detailed calculation or experimental result, and that we have here in this diagram. Last part that we have to do, like similarly for oxygen, we can also do this thing, transfer configuration for nitrogen and bond order for nitrogen as well. So let's just do that as well. So for nitrogen, it has, and do this, we have 10 valence electrons. Right. So if you go with this nitrogen for N2 molecule, what we will have is we will have 1 sigma g to 1 sigma u to. Basically, you just go to this diagram, right? And now this is for the nitrogen. This side is for the nitrogen. Here this side is for the nitrogen side, and this is for the oxygen side. So in the nitrogen, minimum is 1 sigma g. So 2 electrons will go into 1 sigma g, and 2 electrons will go to 1 sigma u. Electron will go to 1 sigma u, and 4 electrons. Now then the next in the energy level is 1 pi u, you can see here. Next is 1 pi u, so we will add 4 electrons here. So 1 pi u, we will add addition rate 1, we will have 1 pi u, we will have 4 electrons, and then in 2 sigma g we can put 2 more electrons, 2 sigma g, and that will cover all the 10 valence electrons. So we just form our ground state, and from the here we can form the bond order, is equals to half of, we have 2 electrons from sigma g bonding, and 4 electrons from pi u bonding, 4, 5, 6, and then 2 from 2 sigma g as well, they are also bonding. So in total we have 8 bonding electrons, and 2 in the anti-bonding orbitals from 1 sigma u. There will be 6 divided by 2 equals to 3. And as you know, this again gives you the bond order 3, and so nitrogen also has a triple bond. So it also shows you that the strength of the nitrogen bond is stronger than the oxygen. This is also this is the problem that we have to do. Now we have still have, I guess we have 20 minutes. So we will quickly discuss the assignment problems as well. So assignment 3 has already been solved, and so we will just quickly discuss all the solutions, and hopefully if you had any doubts that would be clear by this quick discussion. Okay, so the first question is the wave function of a homonuclear diatomic z-axis is the internuclear axis and is given by 3D xz A minus this 3D xz B. Here A and B refers to the location of the two nuclei. How would you characterize the corresponding orbital? So for to solve this question, as has been given here, we know that okay, we have 3D xz on atom A and 3D xz on atom B, and if you go to this homonuclear diatom, so this dxz they are of the basically they are of the same symmetry because they are dxz orbitals, both are same. So we will combine when we will combine both of them, and both of them will have they have the pi symmetry, and here you can see they are so you can how will you so you can say they will give a symmetric pi u orbital as has been shown from this diagram. Okay, yeah, because axis will give you a pi, and then both of them will give you a bonding orbital pi u, because the answer could not be the sigma orbitals, sigma or delta. Then they will give you a pi orbital, and since if you are taking both the xc orbitals, the corresponding molecular orbital will be a bonding orbital, because we know basically you know that the lowest energy orbital will be a bonding orbital, and in the pi case the bonding orbital is pi. That's why the answer is C. Okay, that's why the answer is C, because you have to make a bonding orbital. Sorry, I just so you just have to form the bonding orbital, and this pi u will be your answer, because the orbital will be forming will be a bonding orbital, and it's not going to be a sigma orbital, it's going to be a pi orbital according to the if you see the within the lecture notes, if you see the table, and in pi the bonding orbital is given by u. Alright. Then the overlap integral between two hydrogen atom wave function in S2 molecule is shown as a function of internuclear distance r. Identify the atomic orbitals. Z axis is the internuclear axis. Okay. So here, as has been given in the solution itself, so within this, if you see this overlap integral and how this is changing the radius, the distance between the atom r, option A and C would show non-zero overlap. Okay, A and C option. Now A and C is SS orbital overlap and peak space orbital overlap. At article 0, they will give you because they are the same orbitals, they will give you some overlap, non-zero overlap, which will decrease with increasing r. So and while here you can see at article 0 the overlap is 0, so A and C are not the option. Option D would be 0 for all. Then option D, Px and Py, they will have 0 overlap for all the values of r, and thus while the option B should be 0 at overlap of r. So I guess this is also quite easy. It's from S and PC orbital, as has been explained. Yet 0 overlap at r is your maximum at the intermediate of r. S and PC orbitals. Okay. Then similarly in question number 3, also the shown molecular orbital of H2 correspond to which of the following linear combination of atomic orbitals. And from here also, first of all, you can see that this is going to be a bonding orbital, because there is charge density at r equals to 0. So it could not be these anti-bonding orbitals. And there is a node. Here you can see there are nodes. So it could not be a 1sa, 1sp orbital, and thus it will be answer number C, as has been explained here. And also I guess by eliminations also it was done. And Px, Py, they will always be 0. So S and Pc also give you this result. Now to solve this question, like which of the following is an acceptable non-normalized approximate wave function? Now for this, first we will go with the anti-symmetric part. then we can just directly prove with the antisymmetric. And in this case, if you see 1s1, 1s2, this doesn't give you an antisymmetric wave function. Then this also doesn't give you an antisymmetric wave function. Even this also doesn't give you an antisymmetric wave function. Only this is giving you an antisymmetric wave function, and you can see that as a result it doesn't violate the Pauli exclusion principle as well. So that is your answer D. Then again, similarly, the question that we have solved today in the earlier in the session as well. So when you have to solve this kind of alpha 1 alpha 2, just go to the whatever this is given. So alpha 1 alpha 2 represent s equals to our triplets. So it represent s equals to 1 and ms equals to 1. Right. So this is our alpha 1 comma alpha 2 basically. Alpha 1 alpha 2 is actually just this. As has been given here. So basically our alpha 1 alpha 2 is basically s equals to 1 and ms equals to 1. So if you apply escape square on this, s equals to 1 and ms, so you just solve it like this. Basically you write this as s equals to 1 and ms equals to 1. Now you know that this becomes as h cross square s into s plus 1 times s equals to 1 and ms equals to 1. This will give it to h cross square alpha 1 comma alpha 2. S plus 1 s plus 1 divided as alpha 1 alpha 2. And thus you will get answer 2. Alright. Then next is you have wave function this given by 1s1 3d plus 2 alpha 2 is not a well behaved function for the helium atom because the wave function does not satisfy the okay. So as given, the wave function does not satisfy the indistinguishability and is not antisymmetric. It is not antisymmetric, but the two electrons can have the same. So answer is okay because A is correct. It does not satisfy the indistinguishability of the electrons. In the wave function, there is no asymmetry principle could not be satisfied either with the spin or the spatial part. Now, two electrons cannot have the same spin, so that's not true. We have seen that in the triplet state, they have the same similar spins, and the second electron can be in 3, and the second electron could be in 3D electrons for the helium because they are virtual orbitals, but we can still in the excited state we can go to those orbitals. So that's my answer is A and B. Then what is the electron energy of H2 plus when the internuclear distance is infinite? Now as we have seen, as I said in the session, generally when you have this distribution, these are bi-radical distribution. We know that experimentally the distribution will be by bi-radical dissociation. So if we have this okay, so if we have this this kind of dissociation, this will dissociate into He plus like in the case of H2 molecule also we have this bi-radical dissociation. Each electron goes into the sun charge. So this dissociation it will also happen into a similar manner. So we will have plus charges on both of them. So now this becomes He plus and H plus. It tends to infinity. And the electron energy of He plus, now in H plus there will be no electrons, so no electron. So no electron energy. Therefore there is no electron energy. And there we have single electron, one electron. So the energy He plus will be equals to minus 0.5 times c square That is 0.5 times z, it is 2 to 24, and that will give you 2. So the answer will be -2 components. So that is how it has been solved. Then next is when you increase the bond number of H2 molecule, which of the following happens to the molecular orbitals of water? So this is given. This is given in the class, and the explanations are. If you just see the lecture notes, that is the same. So I will just as given 1b2 and 2a1 are non-bonding. They were non-bonding orbitals. Okay, 1a1 and 2a1 is a non-bonding orbital. Okay, so 2a1 and 1b2 are they were non-bonding, so they will not get changed whatever happens to these bond angles, and those uniform increasing bond angle. The bond interaction between oxygen and H atoms increases in 1b1 with increasing bond angle. So we have the 1b1. So 1b1 was something like this. Yes, so you have this they have this bonding orbital in there. I have to check the diagram actually. I have the diagram. But basically, this is self-explanatory question as has been explained here. So basically what will happen is that for your H2 molecule, as you increase the bond angle, the interaction will decrease because you increase the bond angle, the bond distance you can see, okay, bond distance here was so, and thus the energy will decrease. The energy will decrease if the this interaction this bonds become stronger. Basically, if the bond interaction is becoming stronger, the bond is becoming strengthening. So that's why the answer is D. 2a1 doesn't change, because you can see, or you can just say the energy of 2a1 doesn't change this way. No, and 2a1 increases, that will be wrong, or 1b2 changes, increases, that will also be wrong, and 1b1 increases, but actually 1b1 decreases because your interaction energy is increasing for the bond angles. Okay, and then similarly, okay, now in this this is for the polyatomic question. In the symmetry adapted linear combination for the numerical orbital treatment of H2S, which of the following atomic orbitals of sulfur would not contribute to A1 molecular orbitals? So, as has been shown now for the H2S, okay, this is similar to what was done for the H2 molecule in the class. So for the H2 molecule, as you know, they will have this kind of an anti-bonding. I will just some green, and this is some red. Right? This is your H2 bonding. This is your anti-bonding. 1s minus 1sp. Okay. And you will also have this 1sp plus 1sp. Both are these are your bonding orbitals. That is your bonding orbital. Alright, and similarly for sulfur, you will have sulfur X. You will have sulfur PPY and sulfur PPC. And similarly, you have oxygen, sulfur 2X. Okay, so you just have to solve this question similar to what has been done in the class. And the symmetry adapted linear combination for the molecular treatment of H2S, which of the following atomic orbitals of sulfur would not contribute to the A1 orbital. Okay, so first we will just define which one. So this is the H2 molecule. So basically we know that for H2 we will have this atomic orbital, but instead of using H2's atomic, we use the molecular orbital of this H2, which is 1sa plus 1sp form of H2 plus. Right. Okay. Basically, these are the for the H2 plus for your H2 part, we have like we will take similar to what we have done for H2. So we will take this for the H2 part, and this is for the sulfur part. Now going into this H2 plus bonding orbiter, this H2 plus bonding orbiter. So here you can see that this will have a 2-4 symmetry, E symmetry is already there, 2-4 symmetry is already there. Then it will have these mirror plane about XZ and YZ. Okay, and you can consider XZ here. So this will have the A1 irreducible symmetry. Now in this case there will be no 2-4 symmetry, so it will have either B1, B2, and then if you see the plane with respect to XZ, it is symmetry, but with respect to YZ, this is anti-symmetry. So this one is, so we have the B1 irreducible symmetry. Similarly for oxen 2s, for S we can say it will have the E1 symmetry. For PX you can see this will have the B1 on the table, B1 symmetry. This will have the A1 symmetry, we will have the B1 symmetry. This will have the A1 symmetry. 2px from here it will have the B1 symmetry. Similarly 2py will have the B2 symmetry, and 2pz you can see will have the A1 symmetry. These are the like x, y, z. This basic table gives you the p terms, and this gives you for the g orbitals. Alright. Now what has been asked is that okay, so this is that's a recap of what H2O is done. So it will also have the similar thing, and so basically we will have some wave function of this A1 and psi A1. So similarly we will have some psi A1 is C1 times of surface and everything, but here the question is a little different. So that is as a region, and the symmetry adopted in the condition which are fine would not contribute to A1 molecular orbital. So from just from the characteristic table, it can be seen that PS orbitals, you can see that 3s will contribute to A1. So this is basically how you solve for okay, I guess. Okay, this is for the oxygen part. This is basically for the oxygen part that we have done to S2, and the orbitals will be similar, but it will be like this. For the oxygen part, sorry, so sorry about that. Actually, this is the server. This is 3px. Here this will be 3px and 3py, 3px, 3py, 3pz, and 3s for sulfur. I just want to emphasize that this is similar to the problem. So if you have to do it for 3px, 3py, 3pz, okay. So I just want to emphasize that okay, this could be done, but for this question you don't need to do this. I just want to emphasize that is what was done in the class, and psi1, this you will form your ground state in the similar form. Similar to what you have sulfur 3s, you have C2, 5, 2s for 3s, and similarly you will have, so you will have these orbitals will combine to give a psi1, someone will combine psi b1, what we're turning the H2. So for S3 is also same thing will happen, but in this case it is something that which of the final atomic orbitals of sulfur would not contribute to A1 molecular orbital. So we don't need to go into this for the p orbital and d orbital, and 3s will contribute to the A1, 3px, you can see 3px will contribute to the b1, it will not contribute to this, so this should be the answer. 3d z square you can see for d, it will contribute to A1, and the x square y square they will also contribute to A1. Okay, and the last part of the problem, sorry about this, I just want to explain like the H2s also, that is the same as what you have that we have done in the class for the H2 molecule, but in this question you just have to see the characteristic table, and for characteristic table these are the p for the p orbitals, and this you can put for the d orbitals character table, and sorry, now in the molecular orbital treatment of NH3, what will be the size of the sample determinant if you do not consider, again as we discussed in the session as well, if you consider like if you have for NH3, for nitrogen you will have, as given, you will have 4 atomic orbitals, and for hydrogen you will have the 1 atomic orbitals, so in total you have 7 atomic orbitals, right? And because of this you will have you have to take a linear combination of the 7 orbitals, and thus you will have n plus n secular determinant, and here n is equals to 7, so that's why here n equals to 7, and that's why you will have this 7 plus 7 will be your answer. You do not consider modular orbital, and if we have to consider all, then our secular determinant will be of 7%. This is just a quick overview of the assignment as well, and that's all the time we have for this session.